So in this section, we implicitly defined a nabla operator, and for both 2-dimension and 3-dimension. So how did that work? We defined gradient of f at any point x and y to be partial of f with respect to x, partial of f with respect to y. And then for 3-dimensional space, we did, I'm changing the notation, I'm going with this now. And fy of x and y and z, and fz of x and y and z. It's all partials. It's just that type of partial or this type of partial. And then it looks like that every time I'm just, when I add the nabla, I'm taking the partial with respect to x and y and z. So nabla is sort of this. And we talk about it later in later chapters, but it's nice to think of it this way when you get there. Now, what are the important parts in here? When you define a gradient, I know that gradient of f at point A and B, if it exists, is perpendicular to level curve of level kf at f. This is the level curve that goes through level curve through point A and B. So it's every gradient of 2-dimension is perpendicular to a level curve. Here, because there are 3 of them, I can say that the gradient of f, let's see, let's make this little f, is perpendicular at A, B, and C is perpendicular to level surface of f. Because this time level thing is going to level set, it's going to be level surface. Level surface of f through A, B, and C. Now, a nice thing that comes out of this is that I can say that if I have an implicit function, f of x and y and z equal to c, then I can find a gradient of f at any point A, B, and C, and that is orthogonal to the implicit function at A and B, at the surface of implicit function at A and B and C. That level surface, this is going to be a level surface basically. So that tells me that it's going to be if the tangent plane exists, then this is going to be perpendicular to the tangent plane. That also tells me that I can dot this with x minus a, y minus b, and c minus c, and set it equal to 0 to get the equation of tangent plane. Of tangent plane, if it exists. That exists part is important. Just having partial derivative doesn't mean that the equation exists. And then it tells me about normal line, because that's because gradient of f at a and b and c is orthogonal to the tangent plane. It is in the direction of the normal line. So I can write r of t is equal to point ABC plus t times gradient of f at a and b and c.